Hello class, welcome back. This tutorial will demonstrate you how can we calculate the net benefit using the costs, benefits, as well as the evaluations from confusion matrix. And we will also build cost-sensitive learning models to minimize the costs. First of all, we will first demonstrate how to calculate net benefit. So in our dataset, the target variable is by, and it has two levels, yes or no, and the prediction decisions are associated with some monetary costs and benefits. So, for example, if we predict the cars are bad purchases or bad buys, and they actually are bad buys. So the costs, if we know they're bad buys, we're definitely not gonna purchase them. So the costs for the true positive instances are 0. Well, similarly, if we know that we predict that these cars are not bad buy, which are good buy. So, and they actually are good buys, and we will definitely purchase them. So the costs for the instances that fall into the true negative cell are also 0. Well, however, if we predict some cars are bad buys, but they actually are good buys, so the opportunity cost for passing on a good car is $600. So for those instances fall into the false positive cell, each of them will have a cost equals to $600. Well, in addition, if we predict these cars are good buys, therefore we will purchase them, but actually they're not good buys, so they're bad buys. So the cost for each car that are not able to resell because they're bad buys is $5,000. So now we have this cost table where the cost for each instance in the false negative cell is $5,000, while the cost for each instance fall into the false positive cell is $600. Well, we also have the benefit table. So for example, if we classify these cars are not bad buys, so they're good buys, and actually they are good buys, so the resale benefits for each car is $600. So for each instance fall into this true negative cell, the benefit for each of them is $600. So how can we calculate the net benefit? Well, the net benefit equals to the benefits minus the costs. So we'll use 600 times the numbers of instances that fall into the true negative cell, and minus the cost, which is the $600 times the false positive, and $5,000 times this false negative. So let's look at our codes in our command. So we first use the confusion matrix from the decision tree model. So we used the average value of false positive and false negative, and timed them with $600 and $5,000. So we'll have the average costs for the instances that in the testing dataset, and then we will calculate the benefits also using the average value of true negative. So this benefit is actually the average benefit for the testing datasets. And then using benefit minus cost is the average net benefit, the average net benefit for the instances in our testing data set that is predicted by our decision tree model, because we're going to use naive Bayes model later. So this one is based on decision tree model. It is from the confusion matrix of decision tree model. And decision tree models, because we have 3 models, and these are the average cost net benefits. And we also want to get the net benefit per car, which is per instance in the testing training data set. And we will use this net benefit, average net benefit, divided by the average number of instances inside one testing data set. And similarly, we will also use the average confusion matrix values from the naive Bayes models. And here we use the average false positive and false negative and average true negative. And similarly, we'll also calculate the net benefit per instance. So let's run this chunk and compare their performance financially, like economically. So run current chunk. So we can see that the net benefit for the prediction results from the decision tree model is 45,000, and the average benefit is around $14. However, see the naive Bayes model, we can reach almost 57 net benefit, and the average net benefit per car is almost $17. So financially, we can say that naive Bayes model performs better than the decision tree models. Well, next we will demonstrate how to build a cost-sensitive learning model based on certain algorithms. So there are 2 necessary components when you build a cost-sensitive learning model. The first one is a Bayes model. You can use either decision tree or naive Bayesian or other algorithms or classifiers to build a cost-sensitive learning model. And another component is this cost matrix. While the purpose for the cost-sensitive learning models is to minimize the total cost from the predictor, the final prediction results from your model. So we have this cost table we mentioned before. So as you can see here, the cost for the false negative mistakes is $5,000 for each instance, while the false positive mistake, the cost for the false positive mistake is $600 for each instance. So obviously the mistakes for false negative is more costly than false positive. So we're trying to build a cost matrix to give more cost, more punishment to this false negative prediction. Therefore, it will reduce the instances that fall into this false negative cell. So here we give 2.5 cost to this cell, to the false negative cell, and only 1 to false positive cell. Therefore, the prediction, like the classifier, will predict less level node. Therefore, they will have less instances that fall into this false negative cell. And therefore, to minimize the total cost from the prediction result. So next, let's see how can we implement this cost-sensitive idea into R. So we will use the C50, the decision tree model, as our base model. And the first 2 lines of our commands are constructing this cost matrix. The first line of our command is building a list which include two elements, and the first element include also two values. The first value is predict no and predict yes. So this list will serve as the titles for rows and columns for the cost matrix. So here we use the matrix function to build this matrix. So see here, there are four numbers: 0, 1, 2.5, and 0. Well, these four numbers will fill in the column first. So when you build this matrix, it will look like 0, 1 to fill in the column first, and then 2.5, 0. And the list we create here will be used for the axis titles by assigning it to the dim names, and by telling them we have two rows means we have a 2 by 2 matrix. Well, next let's look at this cost matrix. So as you can see, the first element served as the row title, and the second element are served as the column title. So here you can see we mentioned here before that we want to put more costs, more punishments to the cell false negative. So you can see here for the false positive we have 2.5, and false negative we have 2.5, and for the false positive we have 1. Well, after we build this cost matrix, we will use the similar steps as we did before to build using the for loop to build 3 different cost sensitive models and calculate the average true positive, true negative, and so on. And also we also use the metric function and append the accuracy, precision, recall, and F measure for each model, and append the values to this array called cost total result. Well, in the end, we will also, out of the loop, we will also use row means to get the average accuracy, precision, recall, F measure for these 3 cost-sensitive decision tree models. Well, we also use the similar steps to calculate the net benefit and the net benefit per car, the average net benefit per car for the 3 cost-sensitive learning models. So let's run this chunk and see their performance. So remember we had how much, like the average net benefit for each car in the testing data set is about $17 for the naive Bayes model and $14 for the decision tree models. But see here, we use cost-sensitive learning for decision tree. Now we have almost around $30 for the average net benefit per car. Well, in the end, we also want to compare the results for 3 types of models: decision tree, cost-sensitive learning decision tree, and naive Bayes models. We will also use the row means to get the average accuracy, precision, recall, and F measures from the iterations. And we also want to compare the performance financially. So in terms of cost, we will also compare the values of net benefit per car from different models. So let's run this chunk. Let's see. So in terms of accuracy and precision, recall, and F measures for the class level, no, the performance are similar. But in terms of the precision, recall, and F measures for the class level, yes, which is minority class. Well, for the precision, decision tree models performs the best, and the cost-sensitive learning is performing the worst. While in terms of the recall, naive Bayes model performs the best, while the cost-sensitive learning performs worst. So is the F measure for the yes class. Well, in terms of the cost, financially evaluation, well, you can see here our cost-sensitive learning reaches the highest cost net benefit, average net benefit per car for the instance in our testing dataset, far larger than the values from other two models. So basically that's all we have for this tutorial, and thank you for your time and thank you for listening. Bye.